Testing 1, 2, 3. Right, good. We can start. Right, we continue on section 8.3. Last time we stopped at that problem. So the rule when we integrate that has the power of sine and cosine, we're going to use that. If we have a power of odd on the sine, we let u equal to cosine. And if we have the odd power on the cosine, we let u equal to sine. And if both of them happen to be even, we use the power reducing identities. A lot to go with that. This is the power reducing. And we might have to use Pythagorean identity as well. Right. Before we continue on that, we need to do one more example. Right, 2b6. Right, let's try that. So we have a power of sine and a power of cosine, and usually this kind of problem we will have the same argument of 7x and 7x. Right. So since the power is odd on the sine, we're going to let u equal to cosine of 7x. By the way, it will be extremely helpful if we know that when we have the power, when we write like that, we actually mean sine of kx to the power n. So that power on the whole thing or right in the sine will be equivalent. And also a coefficient times x, we treat that the whole thing as an argument. So in this case, 7x is inside the sine, and then we cube. So we may or may not have to write like this. It doesn't matter. When we have cosine, that the power will be on the outside. It should not be a big deal. Right, like I said. By the way, on the screen is that look a little bit dark. Because I see on the just a second. No, it's fine. Yeah, because my laptop, the display is kind of color a little bit off. Anyway, so. Thank you. Right, so the power is on here. On the side, which means u is equal to cosine. Right, so that's what we have. So we let u equal to cosine of 7x. And we can take derivative. That's good. Derivative of this is negative sine and then multiply derivative multiplied by the coefficient. We did this a lot in the previous section on the integration by part. We use this a lot for derivative. We multiply. Actually, it is right here. So when we take derivative, we multiply by a constant k, and the integral we divide by the constant k. So this is dividing. I mean multiplying, obviously, when we take derivative. Right, move the dx over and divide by that. So we have u and we have dx. So we can do the substitution. Right. Here we have the sine. So we just write like that. Still there. The cosine now, that is going to be u. Dx is going to be this. And now we can cancel the sine. This will have the cube, so that cancel. We have two of them left. Negative 7. Take it outside. Let it stay at the bottom. So we have sine square. And that sine square, once again, we can just put that right here. Instead of the whole thing. It's equivalent. And then u square, negative 7 on the outside, sine cancel, so we just have du. Right. So, there's a little problem here that we have the u square. Everything should be in terms of u. So we have sine square. Right. So what do we do with that? What we can use is the sine square is equal to that. However, if we write like that, the cosine of 2x is not u. What we want is u equal to cosine of 7x. So we need that in terms of u. So we need to write the sine square in terms of the cosine square. And obviously we're going to use the Pythagorean identity. So where we can go to the sine square to cosine square. So let's do that right here. Sine square. The argument doesn't matter. 7x cosine square of 7x equal to 1. So we get sine square equal to 1 minus cosine square of 7x. And we can substitute that in here. And the cosine square is that obviously going to be u square and then multiply it out. U square minus u to the 4th power du. And the rest is simple. That is negative 1 over 7 u cubed over 3 minus u to the 5th over 5 plus c. And finally u is equal to cosine of 7x. So just substitute it back in. So that's what we have. That's fine. So that's where we have sine, cosine. We might have the multiple of the angle, but that doesn't do anything. We still take the derivative, multiply to that coefficient, and then we just proceed like normal. Bottom line is, if the odd power is on the sine, u equal to cosine. If the odd power on the cosine, u equal to sine. So that will be straightforward. Right. Right. We already write this integral out. Except on the cosecant, we write that differently. So this is what we have from last time already. So we're going to use all of this again. But this time, we have integral that have tangent and secant. The review is going to be see the previous note. Yeah. So at the beginning of section 8.3, previously we write all the integrals and the trigonometry identities that we need to use. Right. Now we don't need to write that again. I think I even do this before, but has to one of them again. Let's say if we want to integrate tangent of x, the proof is just write that. It's a ratio like this. Right. So there's some option. Both of them power are odd, so we can let u equal to sine, u equal to cosine. However, what we're going to be easier if we let u equal to cosine. So this is kind of like the trig substitution. No, I mean that should be trigonometric integral. So we check derivative. And there's no dx here. And then we move the dx over. And then divide by the negative sine x. So we have sine x over u and du over negative sine x. Cancel out. Take the negative outside. And integral of 1 over u is ln of absolute value of u and u is cosine. Right. Except what we have here is ln of secant plus c. That's what we have. So surely we can do that too. The properties of the log, I will write that over here. Log of m to the p power. We can take the power outside. That's what we have. So I will take this power back inside. And we have ln of cosine of x to the negative 1 plus c. And actually we can take the negative 1 inside. By the way, we can check the power inside, the power here to there, unless if we have sine of negative 1, that is the inverse. So we cannot write like that. So this is wrong. So everything, any power works except for the negative 1. We cannot take that inside here, because when we write like that, we mean sine inverse. So any power, we can do that, but not on the negative 1. So I will not write the negative 1 here, because that means the inverse of cosine, which is wrong. What it actually is, to the negative 1 is the reciprocal power. So cosine, pronounce space here, but cosine of x to negative 1 is 1 over cosine of x, which is equal to secant of x. and not the cosine inverse. So ln secant of x plus c. Right. So very important that the power -1 will never go to the trig function like this, because that means inverse, and we're not using the inverse here. It is the reciprocal, not the inverse. Right, 2. The secant x. Now the proof for the secant is slightly different. What we actually do is multiply and divide secant x plus tangent x. And multiply on the top. That gives us secant square plus secant x tangent x over secant x plus tangent x. On the last problem, because u is equal to the denominator, it will be easier than u equal to the top. Actually, it will work too, but if you let u equal to sin x, I think, but it will be a lot more complicated. So if there's a choice, choose something inside the parentheses under denominator, like this one. Right. Okay, on this one, if we let u equal to the denominator, usually one of the usual suspect is the denominator or inside the parentheses, inside the radical, on the exponent. Those sorts of things. So we let u equal to secant x plus tangent x. Take derivative. Derivative of secant is secant tangent. Derivative of tangent is secant square. Move the dx over. And divide by that. And substitute this back in. We might not have enough space here, so let's just say that is an integral I, where we continue here. Right, the top still secant square and secant x tangent x. The bottom is u. And then dx is this. That cancel out. I just have 1 over u du. The integral of that is ln of absolute values of u plus c, and finally u is this. bottom line is beginning of the section 8.3, we write out all the integral that we need. So that's all we need. Now the rules. Now, unfortunately, on the power of sine and the cosine, for that, the power of tangent and secant will be a lot more complicated than the law of sine, where we have the power of sine, cosine. For sine, cosine, whatever is odd, we let u equal to the other one. That's easy. The rule for secant and power of secant and tangent are not quite obvious. Number 1. If the power of secant is even, so we will have that integral tangent of something. And if the power of secant is even, then we will let u equal to tangent 2. Now, if the power of tangent is odd, doesn't matter what the other one is, we'll let u equal to secant. Right. And the case that remains we don't have is the power of tangent is when we have the power of tangent is even. And then the power of secant is odd. When we have this, usually we'll try something else. Try something else. Usually Pythagorean. Sometimes there's integration by parts. And usually when we have this case, that is the complicated situation. Right, so secant is even, u equal to tangent x, tangent is odd, u equal to secant. A little less obvious than the other one. Okay, we have the first example here. I'll write that on the next page. Right. Usually we see the line in the note. That means we do that in 2 different ways. So I will fold the paper in half. D. Evaluate. Right, the first one we have integral of secant square tangent x dx. So when we look at this problem, what do we let u equal to? Or do we have to try something else? So we look at here. Power of secant is even. We have that, which is good. So we can let u equal to tangent x. And also, power of tangent is odd. We can let u equal to secant x. Either way works. So that's why we write to do that in two different ways. Right. First, we're going to use this. Power of secant is even. So we let u equal to tangent x. Right, get back to that. Derivative of tangent is secant square move to the x over and divide by the secant square. Yeah, right. Divide by the secant square. And then we can substitute into that integral. So let that integral be the integral I secant square will stay there. Tangent x we let equal to u. And then we have dx is du over secant square. Conveniently, they cancel out. So we just have u du. Integral of that is u squared over 2 plus c. So what we have is u is tangent x. So tangent of x square of course the square we can write right there. Right. So at first, right? So when we have the power of secant is even, let u go to tangent of x. Right. Now we use different method. Now if we have the integral of secant square tangent x dx, the same thing. The power of tangent is r. If that is the case, we'll let u equal to secant x. Right, so we do that. This time, let u equal to secant x. Right, so we do that. Derivative of secant is secant x, tangent x. Move to the x over and then divide by that. So we solve for the x. Now that integral I equal to, right, I will rewrite the problem. We do let u equal to secant x, right? So there's secant square. So if we want to, we can write u square, right? Because u is equal to secant x. That is u square. Tangent x still there. Dx is this. So cancel out the tangent. Right. By the way, secant x is also u. So we have u square, and then du over secant x is also u, right? And that cancel out. U square and u. We just have u du. Will give us u square over 2 plus c. And finally u is secant. So we have secant square over 2 plus c. Right. Now, the question is, both of them are correct, and actually both of them will be the same. Now say why one of them is tangent square, one of them is secant square, right? But actually they are the same. Notice that now I try to show that they are the same. The secant square, remember, we found identity tangent square plus 1 is equal secant square. So we, instead of secant square, we're going to use tangent square plus 1. Yeah, both of them are correct. And both of them are the same, actually. So instead of tangent square, instead of secant square, we use tangent square plus 1. And we can split this in 2, right? Right. So secant square is tangent square plus 1, and tangent square divided by 2 plus 1/2 plus c, right? Now the 1/2 plus c, that's still a constant. So that's why we can just say tangent square divided by 2 plus c. So those are the same. But here we say c1, because obviously that c is different than this c. But it is still constant. Both of them are still constant. So the answer either the tangent square over 2 plus a constant, or secant square over 2 plus another constant. These two constants are not the same. One of them is 1/2 bigger than the other. But when you type this on MyMathLab, they will take E the answer, because they understand that the constant C could be any arbitrary constant, so they are the same. And just different constant. Yeah. So both of them are correct, and both of them are equal to each other, just different constant. And the same thing, we can say sine square right? So in that case, we might have the answer something like sine square we might have sine square plus a constant equal to 1 minus cosine square plus a constant C. The 1 and C is another constant. So, because sine square equal to 1 minus cosine square, if we have the constant C plus 1 is still another constant. So the answer of sine square x plus C equal to negative cosine square plus C. The constant might be different, but in terms of integral, they will be the same. Right, so we have that. Right, the next one, we should go to the next page, because this will take a lot of space. Right. Next we do this one. Oh, I didn't have it. Right. So, you should write this one very carefully, because at the end of the semester, I will ask you take the picture of this note. So here I write the note for myself. I will ask for the integral secant cube. Yeah. So at the end of the semester, I will ask you the note for that part. So make sure you write. You have this. Right, secant cube. This is a classic problem. So let's check. What can we do up to this point? So the rules are here. If the power of secant is even, u equal to tangent of x. This is odd. That doesn't work. If the power of tangent is odd, we don't even have tangent here. So that doesn't work either. So those two doesn't work, meaning that we have to try something else. Right. Once again, the power of secant have to be even, or the power of tangent is odd. Other than that, we have to try something else. This is one of those scenarios. Right. So, now, the way we do this is a little bit less conventional. Instead of the secant cube, I will write secant x times secant square then say, why do we do that? Right. Well, because it works. I hate to say that, but there's some certain type of problem that we have to do some certain things. Kind of like the where we try to prove the integral of secant. Yeah, we have to multiply top and bottom by the something. So that's why the integral is kind of difficult. We have to do enough problem in order to be able to do it. It's not like something that we know the rule and we can do it. The integral, so we have to do a lot of problem. So we see different techniques and different tools. So we have to have a lot of tools in order to do it. So in this case, involve we split like this. Right. Now, usually in the product, in integral, we're going to use substitution. Now we use a lot up here. That is substitution, right? Now, if we know that it's not going to work like this because we don't have even on the secant and odd on the tangent. So if substitution doesn't work, usually we go to integration by parts. So we use integration by parts. In this case, I'm not using the table. Just write the formula. Integration by parts equal to uv minus v du. Because substitution doesn't work, we might try integration by parts because that's still a product. Now, which one do we let equal to u? And which one do we let equal to dv? Right, the question, the add to that, of course, then you said, oh, we know that. We use this acronym, right? But that doesn't work because both of them are trigonometric expression. So which one do we use? Right. So what we actually use is something that is easy to differentiate. We let that equal to u, and something easy to integrate. We let that equal to dv. Right. Now, here's all the integral. Right. We can let u equal to secant, or we can let u equal to secant square. Right. So let's see, what is the integral of secant? Integral of secant is ln of secant x plus tangent x, and integral of secant square is just tangent, right? Because the derivative of tangent is secant square, so integral or antiderivative of secant square tangent. So I'm going to go with this because it is easier to integrate. So meaning that what we do is let u equal to secant x and dv secant square. Because this one is easier to integrate. The u we differentiate u prime. Just say du. Derivative of secant is secant x tangent x du over dx. Move the dx over. dv is that, so v is integral of secant square x dx, which gives us v equal to tangent of x. Integral of secant square tangent x plus a constant c. Integration by part, we just ignore it. So let that integral be I. So we have I we use integration by parts. uv minus integral of v du. uv times tangent x. So that's uv minus v tangent x. Sorry. Have to be very careful. U is secant x. V is tangent x. So that is uv minus v du. So u v du. Right, so that integration by parts. Secant x, tangent x, and then we have tangent times tangent, so that's tangent square. Right, the question is, can we do that? Let's check the rule again. The rule says power secant is even, which we don't have, or the power tangent is odd, we don't have that either. So we still cannot use this rule substitution. Right, so that usually we might try integration by parts, but instead of that, let's try this instead. We have tangent square plus 1 is equal to secant square. So tangent square is secant square minus 1. Right, so we substitute that in here. Right. We have secant x then secant square minus 1. Multiply this out, secant times secant square is secant cube. Secant minus 1 is minus secant. Right, so we multiply it out and then we split. Be mindful with this negative sign. Negative and negative turn to positive. Right. And then I hope that you recognize this term. Is the original problem, which we let equal to I. So that integral we can just say it's integral I And integral of secant is ln of secant x plus tangent x. And we start with the integral I, so we will say I equal to that. Add them on both sides. One I plus another I, we have 2I. And then, that's another C for now. And then finally divide by 2. So the integral is 1/2 secant x tangent x plus ln of secant x plus tangent x, and then plus a constant c. Let me zoom out so we have the whole problem. Still not enough. Right, there. Right. So this is one of the classic problem where we have the secant cube. So that will be integration by parts. So where we let secant cube is secant times secant square, and we have that. And all we do is just integration by parts. Now the execution will take a lot more work because ultimately we end up with the same integral as before, the secant cube. So we move on one side and then we solve for it. Bottom line, that's what the secant cube equal to. Dx. So at the end of the semester, I'm going to ask you for the note of this one. Right. Let's take 5-minute break. We'll continue at 9:05. Right. Before we continue, just want to show you this real quick. So if you log into my MATLAB right now, I just post the sample test. So this sample test, of course, it doesn't count anything. Just to help you get the feeling of what the test will look like. So let's see, how's that look like? When you click on it, let me take the snapshot. Oh, that doesn't work. Sorry. Right. So when you click on the test, you should see this sample test. 4 questions. You have 4 attempts. On the real test, it will not be like this. On the real test, you have 21 questions and only have 2 attempts instead of 4. So and then we just do the problem. So determine if the integral by making appropriate. So we just need to do this one. Notice that this is unlike homework. When you enter the answer, it will not tell you if it is right or wrong. And in that case, we just go to the next problem. Enter something, and then just enter the next problem, and just enter the answer. They will not tell you if it's right or wrong. And at the end, we just click on submit test. And we just enter the prompt, enter the answer, and at the end you submit the test. And I just answer randomly, so that's why all of them are wrong. Like I said, it's not like the homework where they give you the feedback right away if you do it right or wrong. The test, they will not do that. Alright, remember you have 2 attempts, so make sure to use them carefully. And on the test, the time is 2 hours. 21 questions, 2 hours, 2 attempts. I did not post the test yet. I'll do that right after we've finished the class today. But that's how the test is going to look like. You only have 1 shot. I mean, when you type the answer, you will not know if it's right or wrong. Just hit to the next question, enter the answer. At the end, don't forget to hit submit. When you submit, all the answer will be recorded. And then you can see your grade. Right. So that's the homework. I mean, that is the test. Not like the homework. The homework, you know the answer right away when you hit enter. But on the test, you don't. Right. There are 4 attempts. You just want to try 4 attempts on the sample test, but on the real test. So let me write this. For the model test, there are 3 of them, 3 tests. There's a time limit, 2 hours. Number of questions, usually about 20 questions. About 20 of them. And then you have 2 attempts. So that's for all the model tests, not just the test one. I'll post the test one when we at the end of today. Right, and that's the test review. Also on YouTube, you might want to go over that first. Actually, the test review on my MATLAB also, you might want to finish that before you actually take the test. Oh, one more thing. I got this question asked many times. When those test model due? Will be last day of semester. I don't recommend you do all of them on the last day, but you still can do that if you choose to. Right, so that's what we have for the test. Right. Now this one, let's check the rule again. We have the power of secant and power of tangent. Right. What are the rules? Right, rules here. If power of tangent is odd or the power of secant is even, in this case we have neither. So what we can use is either use integration by parts or something else. But it's not going to be substitution, not just substitution. Right. By the way, we did see that on the last problem, where we apply integration by parts. And for that, we're going to use the Pythagorean identities. So, secant square equal to tangent square plus 1. So, tangent square is equal to secant square minus 1. And I substitute into tangent square. Right, and multiply it out. That gives us a secant cube. And a secant. Right, we just did the secant cube. Which is that. Right. The secant cube here equal to 1/2 secant x tangent x plus ln of secant x plus tangent x. That is secant cube. Right. And then the secant is ln of secant x plus tangent x plus the constant c. Now I will multiply the 1/2 into here and here. 1/2 secant x tangent x plus 1/2 ln secant of x plus tangent x minus ln secant x plus tangent x plus c. Notice that these are like terms. We have 1/2 minus 1. 1/2 minus 1 is minus 1/2. So bottom line is we have 1/2 secant x tangent x. 1/2 minus 1 is minus 1/2. Of ln of secant tangent plus c. Right. So that's what we have. Right. So this could be complicated, but when we bring that to secant cube, that long problem give us this, and then so that's what we have. Next, right, that's too easy. Let's change this up a little bit. Let's say instead of secant to the 4th, we have secant to the 4th of 5x dx. I change it up a little bit. So we have the secant of 5x to the 4th power. Right, so check the rules. By the way, it goes without saying on the test, you should have this rule written somewhere so it's easy to reference to. So, power of secant is even, u equal to tangent x. So that's good. That's where we start with. Power of secant is even, u equal to tangent x. So we have u is even. Power of secant is even. We let u equal to tangent of x. In this case, tangent of 5x. Right. Then we take derivatives. Derivative of tangent is secant square. And then we multiply by 5. That is the beginning of section 8.2. Once again, derivative of multiple angles, multiply by that, and integral will divide. Move the dx. And then divide by the 5 secant square of 5x. Still have secant to the 4th. You can either write like that or write that. It doesn't really matter. Dx is this. Right? There are 2 of them, or the square. Cancel with 2 of this. And the 5. Take it outside. We end up with square. Right. Now, of course, we can also write as secant square. I said the power interchangeable. Either you write on the outside or there. Those mean the same thing. Right. It's good and all, but bottom line is we need this in terms of u, where u is equal to tangent. So somehow we have to write this as tangent. And we can do tangent square plus 1 is secant square. And subtract 1 on both sides. I mean solving for tangent, solving for secant. Oh, actually, it is there already. Secant square is tangent square plus 1. Yes, we let u equal to tangent 5x because the rules say if the power of secant is even, we let u equal to tangent of x. It just happened to be 5x, so we let u equal to tangent of 5x. The multiple of angles should not be a problem. Yeah. What matters is going to be the power of secant or the power of tangent, and the rules here very clear. We just have to stick to it, unless on the last case then we have to try something else. Yeah. So because when we see an even power on secant, that means u is equal to tangent, and at the end that should work. Even though if we don't have tangent, we should be able to write that as tangent, which is u. So end up with 1/5 integral of this is u cubed over 3 plus u plus u. 1/5 u is tangent. We have cube of 5x over 3 tangent of 5x plus c. Right. By the way, on my math lab, when you enter something like this, the tangent of 5 cubed, try to enter like this instead of like that, if it doesn't work. So that's why you should do the homework and do the test review first and see what kind of the answer you're supposed to my math lab will take. If it doesn't take that, try this with the parentheses. Right? So when the power of secant is even, we let u equal to tangent. Right, next. But that's too easy. Let's not do that. Try the want to waste paper. So instead of x, let's do 2x. So that should not be a problem when we have multiple angles. So tangent of 2x cube. Either way. Right, now the rules. What the rule says. Power of secant is even. U equal to tangent of x. That's not what we have. What we have is power of tangent is odd, then u is equal to secant x. Right. This example just show that whether we see it or not, it doesn't matter, because we see the power is odd on the tangent. U is equal to secant. The multiple the angle is 2x, so we have to use 2x. Right. Just jump right into it and you write that. It will take care by itself. So let u equal to secant of x. Secant of 2x, sorry. It will work at the end. Right. Take derivative. Derivative is secant tangent. Except this time there's 2x, so we have to multiply by 2. Derivative is where we multiply, the integral where we divide. Yeah, so if we have the rule, if it follows the rule, then we just go with it. If we don't have the rule like the secant cube, that's where the problem is. But we just jump right into it, and then we determine. Right, move the dx over. And then divide that over. Right, so we have u and we have dx. So standard substitution. So the rules that we have for sine, cosine, or for secant and tangent, those are substitution. And if it follows the rule, if the rules, if the requirements are satisfied, this will not be as bad. Dx is that. Yeah, even though we don't even have u in the problem, but it will show up at the end. It will take care by itself. What we can see here is there's a tangent which cancel, give us 2. Right? Don't mind that. So we'll have, let's take the 2 outside. Right. Still have the secant 2x at the bottom though. This might be a problem. And then du. And on the top we have tangent square. Right. Yeah, we need to do something here because we have u equal to secant of 2x. So that is u. Yes, so at least this is u. Yeah, this is u. But what is tangent square? We have to write that as the secant. So we can use, we write that as u. So tangent square plus 1 is secant square. the angle is 2x. And then, so the tangent square, secant square minus 1. Substitute on the top. We have 1/2 secant square over secant du. Right, like I said, even though when we substitute in there's no u, but it will show up at the end. So when we have the requirement are satisfied, just go ahead and make the substitution, and then it will work out at the end, where at the end we should have u in it. Right, so that is secant square, so that will be u square right, and here we can split u square over u minus 1 over u du. U square over u is u, and 1 over u, still 1 over u. Integral of u is u square over 2. And 1 over u is ln of u. ln of absolute values of u. On the test, if there's absolute value, just enter absolute values. The parentheses will not work. Right? And finally, u is secant of 2x. Secant square minus ln of secant of 2x. Cannot simplify any further. And we have that. So, to recap for this section, we have this rule for sine, cosine. Actually, it will be very easy for sine, cosine. Whatever has the power to the odd, u will be equal to the other one. We might have more than cosine of x, we may have cosine of x, cosine of 3x, or multiple of x. In that case, we still do that. The power is what determines. The multiple of x doesn't matter. Right, so the rule will just jump into it, make the substitution, and then simplify. At the end, if u did not show up at the beginning, when we simplify it, we should see u at the end. So that is the rule for sine, cosine. For the power of tangent, the rule for the power of tangent is this. Power of secant is even, u equal to tangent. Power of tangent is odd, u equal to secant. The trick here is when we don't have it. Then usually when we don't have it, try something else. Either using Pythagorean theorem or Pythagorean identity, or sometimes have to use integration by parts for secant and tangent. For sine, cosine, when we have both of them even powers, use reduction of powers. That always work. like this example, when it's even, that reduction of power. Right. Other than that, we finish section 8.3, which should prepare you for the first test. Now we go to section 8.4, which will go to the second test. Right. Right. So section 8.3 is about trigonometric integral. Right. That's section 8.3, trigonometric integral. So the integrals that involve trigonometric expression. What we do in section 8.4 is trigonometric substitution. So there is no trig in the problem, but we have to use the trig substitution. Actually, what I could do is we might could the whole chapter 8 for a separate test. But chapter 8 is very long with a bunch of different iteration techniques, iteration by parts, and then a lot of other things. So that would be too much. So in that case, I split right in the middle of chapter 8. So we don't have less thing to worry about, because that could be complicated. Now we have the integrals involving a squared minus x squared, a squared plus x squared, and or x squared minus a squared. So bottom line is we have a square, x is variable, a is constant. So in this section we have the integral that involving those three things. Right. I'm not sure that those triangle help, but let's see. Let's do it. Look for the blue one. Like I said, I'm not sure that triangle will be helpful, but we'll go back to that in a minute. Right. There will be three cases. Case number 1, I will write a little bit different here, where we have a squared minus x squared. When we have a squared minus x squared, what we do is we will let u, there's no u here, sorry, that's what we call trig substitution. Let x equal to a sine theta. Right, so this rule are clear. When we have a constant square minus x squared, let x equal to that constant times sine theta. Right, and theta is between negative pi over 2 to pi over 2. So quadrant 4 and quadrant 1. Right? So when we see that, use substitution. Now, let's just draw if x equal to this, divide by a on both sides, we have sine equal to x over a. Right? If that is the case, sine is equal to opposite over hypotenuse. That is sine, opposite over hypotenuse. And the equation would be this. So that's why we have the triangle over there. Now, when we write like this, what we have is a squared minus x squared equal to a squared minus a times sine a squared minus a squared sine squared. Factor out the a square, 1 minus sine square. 1 minus sine square is cosine square. So what we have is a square minus x square is equal to a square cosine square. Right. So when we have this case, use that substitution, and this will come in handy. That is case number 1. Now case 2, where we have a square, a constant square, plus x square. In that case, we will let x equal to a, that constant, tangent of theta. That's not a tangent, that is a times tangent. And it will be in the negative pi over 2 to pi over 2. Be consistent, write this in black ink. Now, if that is the case, we can say tangent is equal x over a, and we can draw the triangle. Tangent is opposite over adjacent, so this we have a square plus x square which is this triangle. Right, now we'll go back to a squared plus x squared. A squared. X is a tangent, a times tangent square. So a square tangent square. Factor out a square and 1 plus tangent square secant square. So we have a square plus x square is secant square. Of course, there's a square in front of it. You see that kind of similar to what we have on the note. Case 3. We have x squared minus a constant square. If that is the case, let x be a secant theta, and will be in quadrant 1 or 2, but not pi over 2. So that is when x greater than or equal to a, and this is x less than or equal to a. Now, if x equal to that, so we solve for secant. Is x over a, right? A triangle. Secant is 1 over cosine. Cosine adjacent over hypotenuse. So we have hypotenuse over adjacent, which is the same as this. I mean adjacent. And then this will be square root of x squared minus a squared. For now, that triangle, you might ask why do we need that triangle, but usually for this kind of problem we will need to draw the triangle. We just play it when we see it. We'll use it when we need. X is equal to a secant a square secant square minus a square. Factor out the a square. Secant square minus 1 is equal to a square tangent square. Bottom line is we have x squared minus a squared is equal to a square tangent square. Right. So this unlike the rules of the previous section, we just have to follow exactly as they say. This is called a trig substitution because we let x equal to a trig function, as opposed to what we have earlier called the U substitution. Usually they distinguish these two kind of substitution. One is the trig substitution, the other one is U substitution. Right. I may not have enough space, so let's just go to the next sheet of paper. Right. So what trig substitution do we use? So we have a constant square minus x squared, a constant square minus x squared. So x is equal to a sine theta. Let me rewrite this as phi squared minus x squared. Right. Now, the rule says a constant square minus x squared, so that is u. I mean, not u. Let x be 5 squared, so that's going to be 5 sine theta. So the a in this case is 5, the constant. So always the constant times whatever the trig function is. In this case is sine. Right. So where do we go from here? So obviously for that we're going to need to substitute in here, yes, and then we need to have the dx. So we'll take derivative dx over d theta. Derivative of sine is cosine. Move the theta over, so we have dx equal to 5 cosine theta d theta. So we solve for dx, which is good. Now, what we have is the phi squared minus x squared. So what is that? So 5 squared minus x squared. 5 squared minus x, 5 sine theta. Give us 25, or 5 squared minus 25 sine squared. Factor out the 25. One minus sine squared. 1 minus sine squared is cosine squared. So this is 25 cosine squared. Which if we want to, we can write 5 cosine square. Either way. Right, now we can substitute back into our problem. The integral I equal to square root 5 squared minus x squared. You can write any of this, but let's use this one instead. 25 cosine square of theta. Dx is this. Five cosine theta d theta. Right. Now, of course, for this we can take right as the square root of 25 and square root of the cosine square. Square of 25 is 5. Square root of cosine square is cosine. And then 5 cosine theta. 5 times 5, 25. And then cosine square. Right. Now what's next? What next is we look at the rules. What happens if we have cosine square? So what do we do when we have cosine square? The rule for cosine square. When sine's odd, use cosine, and when cosine's odd, use equal to sine, and this one's even. So we have to use the power reducing identities. So power reducing cosine square is 1 minus 1 plus cosine of 2x over 2. In this case, it is going to be 25 1 plus cosine of 2 theta. So reduce the power and double the angle. Right, split this out. Yeah, take the 25 outside too. And then split 1/2 plus cosine 2 theta over 1/2 over 2. Yeah, we split that. So we split. And then multiply, so we have 25 integral 1/2 d theta, and that the 2 we can write as 1/2 cosine 2 theta d theta. So we split. And then next 25 integral 1/2 is 1/2 theta, and then plus 1/2 integral cosine is sine, but then we have to divide by the 2. Sine 2 theta and plus c. Right. You may ask where this 2 come from. The 1/2, of course it's the 1/2, but that 2 is the integral. When we do the cosine, integral cosine, it's going to be sine. Right? Integral cosine is sine, but this is kx, or we have 2 theta, so we have to divide by 2. That's where the 1/2 come from. So we have 25 over 2 theta plus 1/4 sine of 2 theta plus c. Right. Unfortunately, that's not the end of it. There's a few more. Sine of 2 theta. We have the double angle. Sine of 2 theta is 2 sine theta cosine theta. So we substitute in here 25 over 2 theta plus 1/4 2 sine theta cosine theta plus c. Multiply out, we have 25 over 2 theta. 1/4 times 2 is 1/2 sine of theta cosine of theta. Like I said, it's not the end of it, but I have to zoom out. Right, so we still need to write the answer in terms of x, unfortunately. Right, so what do we have? Back from the beginning. X equal to 5 sine theta. So you can solve for sine theta is equal to x over 5. So this sine theta at the end here, that is x over 5. And to get back to theta, if sine is equal to x over 5, theta will be sine inverse of x over 5. And that's what the theta is, sine inverse of x over 5. That's good. But what is the cosine of x? Cosine of theta, that is. Right. And that's where we draw the triangle. That triangle. Right. Don't worry, I will zoom in. Back in. Sine is opposite over hypotenuse. I mean the first, talking about this graph. I mean the first one. And adjacent will be hypotenuse square, square root of hypotenuse square minus opposite square. Right. So cosine is adjacent over hypotenuse. That's what the cosine is. And so put everything back, we will have 25 over 2 sine in 25 over 2 sine inverse of x over 5 plus 1/2 x over 5 times square root of 25 minus x squared over 5 plus c. Right. So 25 over 2 sine inverse of x over 5, and we have 1/2 5 times 5, so I have x over 25 square root of 25 minus x squared plus c. Right. So there's a lot of work. That's why I want to stop at 8.3 to have the first test. This will go on the second test. The second test, I will try to group this with something less tedious, like this. 75. Okay. Right. So bottom line is, the rule is easy. Where we have a constant square minus x squared, that's going to be trig substitution using sine. And so for the x, substitute that back in. And rewrite everything. The problem should be in terms of theta. Unfortunately, this one is cosine square, so we have to use the power reducing. And when we do the integral, it's happened, we have to use the double angle as well. Even when we have the answer in terms of theta, we still need to rewrite that as the power of x. Right. Let's take I got some frame dropped, so there's a lag obviously, but I think we're back on. I think it just lag on this problem, right? Yeah, it shows we're back to it now. Right. Even the internet cannot catch up on this one. So. Right. Okay, so it's good. Yeah, let me zoom it back in and see what the problem. Oh, too much. Right. So we start with a substitution. A constant square minus x squared. It's going to be that. It's going to be sine. We need to know what the constant is. Have that. And then we're going to solve for the x. Substitute back into the problem. The problem should have everything in terms of theta. And after that, we go to the integral of trigonometric integral. That's why we have in the previous section, where we have a power of cosine even. That is power reducing. Power reducing. Reducing that power. We have this. And then integrate that. Just happened at the end we have a double angle. So double angle. And then at the end we need to write that in terms of x. Right. So keep that in my pocket. Next. Prove that the area of a circle radius A, radius R, is pi r squared. Right. So we know that already. Now just need to prove it. So I'm trying to draw it. A little circle. So, circle. And then the hint equation with circle. Radius R, center 0, 0. The center is at the origin. So it's x squared plus y squared equal to r squared. Now if we solve for y, x squared plus y squared equal to r squared. So r squared, y squared equal to r squared minus x squared. And we'll take the square root on both sides. Plus or minus. And that is the equation of a circle. So I have two of them. We have the upper half is y equal to square root, positive square root of r squared minus x squared. We have the lower half y equal to negative square root of r squared minus x squared. Right. So the area by the way, since the radius is r, this is negative r and that is positive r. Here 0. So we have r is the radius. So negative r to r. So the area will be the integral from negative r to r. And we have the function above minus the function below. The function above r squared minus x squared the function below is negative r squared minus x squared. Negative negative is positive. So the area equal to negative r to r. Negative positive. So we just have r squared minus x squared plus r squared minus x squared. Will give us 2 times r squared minus x squared dx. By the way, we might don't have to do it like this. We can also use this. Since this is a circle, so it's symmetry. We just do the upper half. If we do the upper half, we just have right the upper half of circle, and then we multiply by 2, give us the whole circle, right? So there's 2. Now even better, instead of do the upper half, we only do a quarter of it. So in that case, the area can also be 4 times. We only go from 0 to r here. Yeah. So in terms of the area, you can do that for upper semicircle or just a quarter of a circle. And in that case, we have to multiply back by 4. Either way works. I'm going to stick with this. I will take out the 2. Right. Now this problem will look like this, except R is going to be 5. Right? Look exactly the same. Ignore that, but we have the limits. Right. So if R is 5, now compare to the last problem. Let me write this again from the previous problem. From previous example. Integral of 5 squared minus x squared dx equal to 25 over 2 sine inverse of x over 5 plus 1/2 times x over 25 square root of 25 minus x squared plus the constant c. So that's what we have. Now all we do is replace the r by 5. Now we'll replace r into 5. So that integral will be 2 times 25 will be 5 squared. So we have r squared over 2 sine inverse of r of of 5 over r. Right? We just replace r into 5. 25 will be r squared plus 1/2 x this is x over 5, so we still have x. Sorry. X and then x over 5, 25 will be r squared minus r squared. Keep doing that. 25 is r squared and r squared minus x squared. Right. And this one we have the limit, so we'll go from negative r to r. Sorry. So 25 r squared, 25 r squared, and 5 is r. Right. Now we will substitute in the r and the negative r. Put in r here for x. So r to this x and r to this x. And now we put in 2. I'll put negative r into that cosine. Right. Now put negative r into x. So that r still r square sine inverse. Now put negative r into x. Negative r into x. And negative r into x. Right. Actually, this simplifies a lot later. First, r square minus r square, so that is 0. That's good. Also, r square minus r square here, so that goes to 0. Now we just have this. Now, what is sine inverse? Right. So we have the calculator there, and finally we use it. Right. I will keep things in radian. So what is sine inverse of 1? If it is in radian, sine inverse of 1 is that. So what is that? How about in degrees? Sine inverse of 1. Right, 90 degrees, which is pi over 2. And this sine inverse of negative 1. Negative 90 degrees, so negative pi over 2. So after both of that, we will have 2 r squared over 2 times pi over 2. Subtract 2 r squared over 2 times negative pi over 2. When we multiply this out, 2 and 2 cancel out. We have r squared times pi over 2. And this cancel out as well. Negative and negative cancel out as well. Have pi squared pi over 2. Common denominator. By the way, I'm going to write as pi r squared instead of r squared pi. And add them, we have 2 pi r squared over 2. Would end up cancel out the 2 pi r squared. So this is a proof showing that the area of a circle is pi r squared using calculus. Right. So equation of a circle that split into a positive and a negative, and then set up the area. And instead of doing that, it is like what we have previously, but this time we substitute r into 5, and we have that would end up being that integral. Right. Remember, this part will be on the second test, section 8.4, that is. Right, try another one. Hopefully it will not be as complicated. always, usually when we have the integral like this, I've moved the dx on the way back. And we can rewrite this as 4 square right. Now, what is the rule for the substitution? Trigonometric substitution. Right. The rule says when we have something square, a constant square minus x square, the substitution is x equal to a sine theta. So in that case, 4 sine theta. So that's trig substitution. Right, then we just take the derivative. Dx over d theta equal 4. The derivative of sine is cosine. And then move the d theta. So dx equal to 4 cosine theta d theta. And we can substitute in for dx. Next, we have 4 square minus x square. Just want to be consistent. Right, I use orange in 4 square minus x square. X is 4 sine. So 4 square. And that is 4 square again. Sine square. Factor out the 4 square. Cosine square plus sine square is 1. So 1 minus sine square is 4 square cosine square. And we substitute in here. So that's why usually in the substitution over there, when we use this substitution, a minus x squared, actually it's better in my notes. Better here. Oh, here. So when we use that, we're going to have, after we use the substitution, we will have a squared minus x squared equal to that. So it's always like that. And at the end, we might need to draw a circle, the triangle. Right. So that integral is I. Just want to be consistent with what I wrote earlier. Right. 1 over that part is going to be 4 square cosine square to the 3/2, and dx is 4 cosine It might not be that bad. Right. By the way, because of the 3/2 power, it will be much better if we write it like this. 4. And we take the square on the outside. Yeah, just use that instead. And after that, we'll raise to the 3/2. Right. Integral 1. The 2 and the 3/2. 2 and 2 cancel out. We have the 3. Two and 2 cancel out, so that's a 3. And then 4. Right? Cosine 4 cube is 64. The cube go to the cosine. And that's what we have. Now, the 4 is constant on the top. 64 constant at the bottom. That's easy. Right. Cosine and cosine cube cancel out. A cube cancel. We still left with a square. Four over 64 is 1 over 16. 1 over cosine square. How do we integrate that? Luckily, 1 over cosine is secant. So this is just secant square. Right? Yeah, this should be easy. 1 over cosine is secant. So that square, so that's secant square. Right, integral of secant square. Integral of secant square is tangent. Because the derivative of tangent is secant square. So that's what we have. Except the answer need to be, I don't know why we'll go back to x. No, we still have theta, right? Sorry, yeah, we should have theta. I don't know why I go back to x. We do need to go back to x though, but not like that. So that should be theta. Sorry, theta. Right. Now, what we have is here. If that is the case, we can say sine of theta is x over 4. So usually for here we have to draw the triangle again. Sine opposite over hypotenuse. So the equation will be 4 square minus x square, square root of that. And then tangent here is opposite over adjacent. Instead of tangent, we have x over square root of 4 square minus x square, which is 16 also, plus c. Right. So it's not as bad as the other one. But usually when we have the trig substitution, we're going to have this part and we have to draw a triangle. So that's why in the note. Yeah, thanks. Yeah, sure, guys. That should be theta, not x. Yeah. Yes, so usually we have that substitution using that formula and that triangle. And so we have all three of them. That substitution, that formula, and that triangle. So that's where we have the first case, a constant square minus x square. Yeah, sorry. This also theta. So the only way we go back to from theta back to x is using the triangle. Yeah, so thanks. Example 2. Evaluate. So when you take the test, the second test, I recommend that you have this part reference somewhere. So actually, calculus 2 is one of, I said calculus 2 is the most difficult calculus out of the 1, 2, and 3. It's not that difficult. The difficult part is it have a lot of rules, and usually study in very limited time, so we don't have enough time to practice and to get used to all the formulas. So that's what makes it difficult. But there's some certain things and there's some certain rule we applied, so it's not that bad. If we know the rules. Right, talking about the rule. This time we have 9. So let's write that as 3 square and move the dx to all the way to the back. Right, let's write like that. Right, the rules. Yes, when you go to calculus 3, it should be a lot easier than this. There's a lot of rules that we have to worry about. On top of that, all the derivative and the integral table, you have to know all of that. So even though if you take this class as a lecture class, on the test you have like 1 or 2 pages of formulas. Yeah, this one will be difficult if we take the test without anything to reference. Right, so we write like that. So the rules. What if we have a constant square plus x square? Okay, exactly here the constant is 3. So let x equal to 3 times tangent of theta. Yeah, that. Where we have a constant square plus x square. Like I said, most of this they follow some certain rules, and so we going to use that. Right. Then we'll take derivative. Oh, by the way, the good thing about this is after this section we go to completely different things. So unlike calculus 1, this section build to the next one and build to the next one. If you don't know it, that is a problem. At least on Calc 2, if for one section you don't get it, you still the rest of them you still be able to do well if you get it. Like each one is kind of separate things. I will have integration by parts, and then the trigonometric integral. This one is trig substitution. The next one is partial fraction. Completely different things. That makes it difficult, but at the same time, if we don't get one section, it's not the end of the world. But on this one, constant square plus x square, that's substitution. At least we have to know that. Right, derivative of tangent, secant square. Move the d theta. So we have the x, and then we have the dx. Next, we're going to find out 3 square plus x square. Three square plus 3 times tangent theta. 3 square, 3 square, tangent square. We can factor out the 3 square. And we have 1 plus tangent square. Right. 1 square plus tangent square, secant square. So we have 3 square plus x square equal to 3 square secant square. It's a rule we have earlier. When we have that rule, we should have this. 3 square secant square. Exactly as a square secant square. Right. Now we substitute back in here. I should not put a square here. It will be simplified a lot. Right. 3 square plus x square. We're going to use 3 square secant square. And dx is this. right? Integral 3 square is 9, 9 square is 81, a square and a square, so we have secant to the 4th power. Never mind, just write like that, square. Now, secant square cancel with the secant square, so we don't have the square here. So secant square times secant square, and one of them cancel out. 3 on the top, 81 at the bottom. And secant square cancel, we have one of the secant square at the bottom. Right, 3 and 81, so it's going to be cancel out 1 over 27. And 1 over secant square, we're going to use just like what we did. 1 over cosine square is secant square, and so 1 over secant square is cosine square. Well, I lied. We definitely need the previous section. For cosine square, because of the even power, we have to use reduction of power, or power reduction. This would be a lot better if we don't have the square at the bottom. Right. Keep going with this. 1 over 27. And we're going to split this in 2. And we split the integral 1 over 27 1/2. And integral 1/2, so just 1/2 of theta. And integral of 1/2. Cosine of 2 theta is 1/2 sine of 2 theta. Right. But that's not the end of it. There will be a lot more. Here we have the double angle. Right. One half and 2 cancel out, so we have 2. 1/2 cosine theta. So there's a lot of practice in this thing, but at least when we see the problem, we know that the substitution is going to be that. And then two things will happen. First, because we need to simplify the x, and the second, we need to do that. And most of the time, we're going to need to draw the triangle. So tangent is equal to x over 3. Opposite over adjacent. And then finally, let me zoom out. Finally, the theta here, we can solve for it too. Theta equal to tangent inverse of x over 3. So we have tangent inverse of x over 3 here. The sine opposite over hypotenuse. The cosine adjacent over hypotenuse. And then we simplify. So don't get too hung up with the rest of the problem. The focus here is, of course, do we know what substitution do we use? Constant square plus x square, that is the tangent. So for the x and so for that, those two have to be there. And then when we substitute back in the problem, we should have the integral of the trig. Now this is like the previous section. And we do all of that, and the rest, it just happened to use the reduction of power reducing, and we use that, and then we integrate. Have to use, usually when we have the power reducing, it will follow immediately with the double angle. So those usually goes together. And then finally we go back and we draw a triangle to figure out everything in terms of x. Right. So at the end, the answer will be 1 over 27 1/2 tangent inverse x over 3 plus 1/2 3x square root times square root. Right. So can even fit the whole problem in one screen. Yeah, like that. So what we have here will not be on the first test, and what I put on the problem on the second test will be a lot simpler than this. Those kind of problems usually kind of complicated. You probably will see something some more like this. So it's not that as complicated. as we see here. Right. So at least we know that the rules that we follow here are very clear. A constant square minus x squared, that's sine. Constant square plus x squared, that's tangent. And x squared minus a constant square, that's secant. So at least we have to know what case do we have. Well, we know that, find out dx, and so forth, that terms. Most of the time we need a triangle. Right. We run out of time, so we stop here. I will post the test one here. I mean after this. By the way, highly recommend that you at least go to the sample test once to see what the test will look like, and then you can check the test one. Right. Once again, this is what we have for the test one, or for every test. Right. Do we have any question before I close this? Turn off the stream. I end the stream, I should say. Right. If not, I will end the stream here. Good luck on the test. Like I said, you don't have to do the test now. Just go over the review first. Get used to it. Take the sample test and see what the test will look like. And then go to take the test. Remember, you have 2 attempts on the test. So take the first attempt. Yes, so that's why at least you know that on this test it is open note. So at least you have something you refer to. Right. Yeah. So like I said, section 8.4 will be on the next test, because I know there will be a lot of rules. So I try to don't put everything on one test. So only up to section 8.3 for the first test. This section 8.4 will be on the next test. Right.